Right now, light is racing past you at 670 million miles per hour. Nothing in the universe can catch it. Not rockets, not particles, not even the fabric of space itself can push matter beyond this cosmic barrier. For centuries, scientists assumed this was just a property of light. Then Richard Feynman cracked open reality and discovered something that should terrify you. The speed of light is not a speed limit for light. It is the speed limit of causality itself. It is how fast reality can update. It is the maximum rate at which the universe can communicate with itself. Every atom in your body obeys this law. Every thought in your brain is constrained by it. And what Feynman found explains why breaking this limit would unravel existence itself. If you want to understand the deepest secret governing reality, something that connects quantum mechanics to the structure of space-time itself, hit that like button and subscribe. This journey may just change how you see the universe. Now, get yourself comfortable. Let's begin. Galileo Galilei climbed a hillside outside Florence in 1638, carrying a lantern and an impossible ambition. He wanted to measure the speed of light. His assistant waited on a distant hill with an identical lantern, instructions memorized, timing rehearsed. The experiment seemed elegant in its simplicity. Galileo would uncover his lantern. The moment his assistant spotted the flash across the valley, he would uncover his own lantern in response. Galileo would measure the delay between sending light outward and receiving light back, divide the round-trip distance by the elapsed time. Calculate the speed. The logic was flawless. The execution was perfect. The result was nothing. No matter how far apart Galileo positioned the lanterns, no matter how precisely his assistant responded, the returning flash appeared instantaneous. Light seemed to cross any terrestrial distance in zero time. Galileo repeated the experiment at greater separations. He recruited assistants with faster reflexes. He refined his timing methods. Every attempt produced the same maddening result. The response appeared immediate regardless of distance. Galileo concluded that either light travelled infinitely fast or it moved so quickly that human perception could never detect its finite speed across earthly distances. He suspected the latter, but could not prove it. His instruments and his era lacked the precision needed to capture something that circles our entire planet 7 times in a single heartbeat. The problem was not Galileo's method. The problem was scale. Light travels at approximately 299,792 kilometers per second in vacuum. At this velocity, light crosses a 1-mile gap in about 5 microseconds. Human reaction time measures around 250,000 microseconds. Galileo was trying to measure a 5 microsecond delay using instruments with 250,000 microsecond precision. The signal drowned in noise before it could be detected. Measuring light speed required distances vast enough to accumulate detectable delays. Earth was too small. The solution would come from the heavens, from an astronomer tracking moons around a distant planet, from a delay that accumulated not over miles but over hundreds of millions of kilometers. Ole Rømer arrived at the Paris Observatory in 1672 as a young Danish astronomer eager to make his mark. His assigned task seemed routine: track the orbital motions of Jupiter's moons, particularly Io, the innermost of the 4 large Galilean satellites. Astronomers used Io's eclipses behind Jupiter as a cosmic clock, timing when the moon disappeared into the giant planet's shadow and when it emerged on the other side. Rømer noticed something strange after months of careful observation. The timing of Io's eclipses drifted throughout the year in a predictable pattern. When Earth's orbit carried it closer to Jupiter, the eclipses occurred earlier than his tables predicted. When Earth swung to the far side of its orbit away from Jupiter, the eclipses arrived late. The discrepancy accumulated to roughly 22 minutes across the full diameter of Earth's orbit around the Sun, Other astronomers attributed this drift to imperfections in the orbital calculations. Perhaps Io's orbit was not quite as regular as assumed. Perhaps Jupiter's gravity created subtle variations that the models failed to capture. Romer considered these explanations and rejected them. The pattern was too consistent, too directly correlated with Earth's changing distance from Jupiter. In 1676, Romer announced his revolutionary interpretation. The eclipses were not occurring early or late. They were happening exactly on schedule. What changed was how long the light carrying news of each eclipse took to reach Earth. When Earth was closer to Jupiter, the light had less distance to travel and arrived sooner. When Earth was farther from Jupiter, the light needed more time to bridge the increased gap. This meant light had a finite speed. Romer calculated this speed by dividing the diameter of Earth's orbit by the accumulated time delay. His result was approximately 220,000 kilometers per second. This estimate was roughly 26% too low, partly because the precise diameter of Earth's orbit was not yet well established, and partly because his timing measurements contained small errors. But the magnitude of his achievement dwarfed these imperfections. Romer had proven that light was not instantaneous. It traveled at a specific, measurable velocity. Information about distant events required time to reach observers. The universe operated with built-in communication delays that depended on distance. This discovery carried profound implications that would take centuries to fully appreciate. If light takes time to travel, then looking at distant objects means looking backward in time. The sun we see is the sun as it existed 8 minutes ago. The universe we observe is a patchwork of different moments, each region frozen at a different point in its history depending on its distance from Earth. Romer's measurement also suggested something peculiar about the nature of light itself. Its speed was extraordinarily fast but fundamentally limited. This limit seemed arbitrary. Why should light travel at exactly this velocity and not some other value? What property of the universe determined this specific number? These questions would haunt physics for the next 2 centuries, while scientists refined Romer's measurement with ever-increasing precision. James Bradley discovered stellar aberration in 1728 and used it to calculate light speed within 1% of the modern accepted value. The apparent position of stars shifts slightly as Earth orbits the Sun, not because the stars move, but because Earth's motion affects the angle at which incoming starlight is received. This aberration depends directly on the ratio between Earth's orbital velocity and the speed of light. Hippolyte Fizeau achieved the first successful terrestrial measurement in 1849 using a rapidly rotating toothed wheel. A beam of light passed through a gap between teeth, travelled to a distant mirror, and returned. If the wheel rotated at just the right speed, the returning beam would be blocked by the next tooth. Knowing the wheel's rotation rate and the distance to the mirror allowed Fizeau to calculate light speed with impressive accuracy. Léon Foucault improved on Fizeau's method using a rotating mirror instead of a toothed wheel in 1850. His measurement agreed closely with celestial observations, confirming that light travelled at the same speed whether measured on Earth or across the solar system. Albert Michelson would later refine rotating mirror techniques to extraordinary precision, eventually winning the Nobel Prize, partly for his meticulous determinations of the speed of light. By the late 19th century, physicists had established light speed at approximately 299,792 kilometers per second in vacuum. The measurement precision reached parts per million. This value appeared in equations throughout electromagnetic theory, always in the same form, always with the same magnitude. Scientists began to suspect this number was not just a property of light, but something more fundamental about the structure of reality itself. The prevailing theory of light in this era treated electromagnetic radiation as waves propagating through a medium called the luminiferous ether. This invisible substance supposedly filled all of space, permeating the vacuum between planets and stars, providing the medium through which light vibrations traveled. Just as ocean waves require water and sound waves require air, light waves supposedly required ether, The ether hypothesis seemed logically necessary. Waves, by definition, are disturbances in some medium. They cannot exist as disturbances in nothing. If light was a wave, it must wave through something. The ether provided that something, an all-pervasive cosmic substance with unusual properties, it had to be rigid enough to support waves traveling at enormous speeds, yet tenuous enough to offer no resistance to planets moving through it. If ether existed, Earth's motion through this cosmic medium should be detectable. As our planet orbits the Sun at approximately 30 kilometers per second, we plow through the stationary ether like a ship through calm water. Light traveling in the direction of Earth's motion should effectively move slower relative to us. Light traveling perpendicular to our motion should be unaffected. Light traveling opposite to our motion should effectively move faster, pushed along by our tailwind. This ether wind effect should produce measurable differences in light speed depending on direction. The expected magnitude was small, only about 1 part in 10,000, but late 19th century precision instruments could detect such differences. The experiment that would test this prediction would become the most famous failed experiment in the history of science. Albert Michelson was obsessed with precision. He had already made his name measuring light speed with unprecedented accuracy. In 1887, he teamed up with chemist Edward Morley to build the most sensitive optical instrument ever constructed. Their goal was to detect Earth's motion through the luminiferous ether once and for all. The Michelson-Morley interferometer split a beam of light into 2 perpendicular paths using a half-silvered mirror. One beam travelled parallel to Earth's orbital motion. The other travelled perpendicular to it. Both beams bounced off mirrors and returned to recombine at the half-silvered mirror. If the 2 beams experienced different light speeds due to the ether wind, they would arrive slightly out of phase, creating an interference pattern of light and dark bands. Michelson and Morley mounted their apparatus on a massive stone slab floating in a pool of mercury. This allowed them to rotate the entire experiment smoothly, without vibrations that might disturb the sensitive optics. They could orient the interferometer at any angle relative to Earth's motion and observe whether the interference pattern shifted. The precision of their instrument exceeded requirements by a comfortable margin. If the ether wind existed at the expected magnitude, the resulting fringe shift would be clearly detectable. Michelson and Morley conducted measurements at different times of day and different seasons of the year, sampling various orientations of Earth's motion through space. They found nothing. Absolutely nothing. The interference pattern remained rock steady, regardless of the instrument's orientation. The speed of light was identical in all directions to within their measurement precision. No ether wind existed because the ether itself did not exist. This null result threw theoretical physics into crisis. Light was demonstrably a wave. Waves require a medium. Yet the medium light supposedly travelled through showed no sign of existing. Something was fundamentally wrong with how physicists understood the nature of electromagnetic radiation. Several theorists attempted to rescue the ether hypothesis through increasingly contrived mechanisms. Perhaps Earth dragged ether along with it, eliminating relative motion at the surface. Perhaps objects moving through ether contracted slightly in the direction of motion, exactly compensating for the expected light speed differences. These explanations worked mathematically, but felt like desperate patches rather than genuine insights. The resolution would come from an unexpected source. A 26-year-old patent clerk in Bern, Switzerland, had been pondering these puzzles since his teenage years. Albert Einstein approached the problem differently than his contemporaries. Instead of trying to explain why the ether was undetectable, he asked what would happen if there simply was no ether, and light truly travelled at the same speed for all observers, regardless of their motion. Einstein later recalled a thought experiment that haunted him since age 16. What would he see if he could chase a light beam and catch up to it? If he travelled alongside a photon at light speed, would the electromagnetic wave appear frozen in place? Would he observe a stationary oscillating field suspended motionless in space? Maxwell's equations, which governed electromagnetic phenomena, suggested this was impossible. The equations predicted electromagnetic waves must always propagate at one specific speed. They contained no provision for stationary light or light moving at arbitrary velocities. A frozen electromagnetic wave would violate the mathematical structure that accurately described every other electromagnetic phenomenon scientists had ever observed. Einstein made a bold choice. Rather than assuming Maxwell's equations were incomplete or that light somehow behaved differently under extreme conditions, he accepted their prediction at face value. Light always travels at the same speed, not because of some property of light itself, but because of how space and time work. In 1905, Einstein published a paper titled On the Electrodynamics of Moving Bodies in the journal Annalen der Physik. This 30-page paper, containing no citations and emerging from a patent office rather than a university, would reshape humanity's understanding of reality itself. The paper began with two postulates stated so simply they seemed almost obvious. First, the laws of physics are identical in all inertial reference frames. An inertial frame is simply a perspective moving at constant velocity without acceleration. Someone floating in space and someone riding a train at steady speed should observe the same physical laws operating in their environments. Second, regardless of their motion relative to the light source, a beam of light approaches you at the same velocity whether you rush toward it, flee from it, or stand perfectly still. This constancy is not an approximation or an idealization, it is an exact statement about how light behaves. These postulates appear almost trivially true when stated plainly. Of course, physics works the same everywhere. Of course, a fundamental constant like light speed should be truly constant. Yet accepting both statements simultaneously demolishes intuitions about space and time that humans had trusted for millennia. Consider what the second postulate really means through a concrete example. You stand stationary while a beam of light passes you at 299,792 kilometers per second. Your friend flies toward that same light beam at half-light speed, 149,896 kilometers per second. Classical physics says your friend should measure the approaching light at the sum of velocities, 449,688 kilometers per second. Einstein said no. Your friend would measure exactly 299,792 kilometers per second. The same value you measured despite moving toward the light at tremendous speed. Now your friend reverses direction, flying away from the light beam at half-light speed. Classical physics says the light should catch up slowly, appearing to approach at only 149,896 kilometers per second. Einstein said your friend would again measure exactly 299,792 kilometers per second. This seems impossible. How can the same light beam have identical speed relative to observers moving at different velocities? Something has to give. Something has to adjust to make these contradictory seeming statements compatible. What gives is space and time themselves. Einstein showed that space and time are not independent, absolute quantities fixed uniformly throughout the universe. They are intertwined aspects of a single four-dimensional structure called space-time. Your motion through space affects your experience of time. The universe maintains light speed constancy by dynamically adjusting space and time for each observer. Time dilation is the first strange consequence. Moving clocks run slower than stationary clocks. This is not a mechanical effect or an illusion. Time itself passes more slowly for observers in motion. The faster you move relative to some reference frame, the slower your time flows compared to that frame. At everyday speeds, time dilation is unmeasurably tiny. A commercial airplane flying at 900 kilometers per hour experiences time dilation of roughly 1 part in 10 trillion. You would need to fly continuously for thousands of years before your watch fell 1 second behind a ground-based clock. But at speeds approaching light, time dilation becomes dramatic. At 90% of light speed, a moving clock runs at less than half the rate of a stationary clock. A year of Earth time compresses into about 5 months of shipboard time for travelers moving at this velocity. The effect intensifies further as velocity increases, with time slowing ever more dramatically as objects approach the cosmic limit. The mathematical relationship is captured by a factor physicists call gamma. This factor equals 1 divided by the square root of the quantity 1 minus velocity squared over light speed squared. When velocity is 0, gamma equals 1 and time flows normally. As velocity approaches light speed, gamma increases without limit toward infinity. At exactly light speed, gamma becomes infinite. Time stops completely. A photon traveling at light speed experiences no elapsed time regardless of how far it travels. The billions of years separating the emission of cosmic microwave background radiation and its detection by your eye is, for the photon, instantaneous. Zero elapsed time, distance without duration. This is why massless particles can travel at light speed, while massive particles cannot. Photons have zero rest mass. They do not accelerate to light speed. They are created already moving at light speed, and physically cannot exist at any other velocity. A photon cannot slow down. If it somehow lost velocity, it would cease to exist entirely. Photons are fundamentally different from everything else in the universe. They either move at exactly light speed, or they do not exist at all. Length contraction is time dilation's spatial counterpart. Moving objects shrink in the direction of motion. A meter stick flying past you at high speed measures shorter than an identical stationary meter stick. This contraction is not optical illusion or physical compression. Space itself contracts for moving observers. The contraction factor is the same gamma that governs time dilation. At 90% of light speed, a meter stick contracts to less than half its rest length in the direction of motion. The shrinking accelerates as velocity increases, with objects contracting ever more severely as they approach light speed. Time dilation and length contraction combine in precisely the way needed to keep light speed constant for all observers. When you move toward a light beam, your time slows down and your measuring rods contract. These distortions exactly compensate for your velocity. You measure distances differently. You measure time intervals differently. The ratio of distance to time, which defines speed, remains unchanged. The mathematics encoding these relationships is called Lorentz transformations, equations that translate measurements between different reference frames. Hendrik Lorentz actually discovered these transformations before Einstein, while trying to explain the Michelson-Morley null result through ether-based mechanisms. But Lorentz viewed his equations as mathematical tricks, describing how ether interaction affected matter. Einstein revealed these equations described something far more profound. They were not corrections applied to measurements. They were accurate descriptions of how space and time actually behave. The universe really does adjust distances and durations depending on the observer's motion. Lorentz transformations are not artifacts of measurement. They are the truth about space-time itself. The equation that captures the deepest connection between space and time emerged from Einstein's framework with elegant simplicity. E equals mc squared. Energy equals mass multiplied by the speed of light squared. This equation is often misunderstood as a formula for nuclear weapons. It does explain why nuclear reactions release such enormous energy from small amounts of matter. But its true significance runs far deeper. The equation states that mass and energy are the same thing measured in different units. The speed of light squared is simply the conversion factor between these units. Consider the magnitude of this conversion factor. Light speed squared equals approximately 9 times 10 to the 16th power meters squared per second squared. Multiplying even a tiny mass by this enormous factor yields tremendous energy. 1 kilogram of matter, if completely converted to energy, would release about 90 quadrillion joules. This exceeds the annual energy consumption of a medium-sized country. Mass is concentrated energy. Energy is dispersed mass. They are not merely interchangeable under extreme conditions. They are fundamentally identical, different manifestations of the same underlying reality. The speed of light appears in the conversion factor, not because light is somehow special, but because light speed represents the fundamental relationship between space and time in our universe. This relationship explains why the speed of light appears throughout physics in contexts having nothing to do with electromagnetic radiation. It emerges in equations governing gravity, particle physics, quantum mechanics, and thermodynamics. Speed of light is misnamed. It should be called the speed of causality, or the speed of spacetime. Light merely happens to travel at this speed because photons are massless. Scientists have tested special relativity with extraordinary precision since Einstein published his theory. Particle accelerators routinely create particles traveling at more than 99% of light speed. These particles experience exactly the time dilation and momentum increase that Einstein's equations predict. Every experiment confirms that the speed of light is absolute. Every test validates that space and time adjust to maintain this constancy. Relativity is not a theoretical framework awaiting confirmation. It is established fact, verified countless times across more than a century of precision measurements. Yet Einstein's theory describes what happens without explaining why. Why is the universe structured this way? Why does space-time have these particular properties? Why is the speed of light exactly 299,792 kilometers per second and not some other value? Einstein showed that light speed is the cosmic speed limit and demonstrated how space-time enforces this limit through time dilation and length contraction. But he did not reveal why the universe demands this enforcement. That understanding would require decades more work, new mathematical frameworks, and a physicist named Richard Feynman who could visualize quantum reality in ways no one else had imagined. The answer lies in the quantum mechanical structure of reality itself. They explore every possible path simultaneously, and the mathematics that governs this exploration makes faster-than-light motion not merely difficult or prohibited, but literally meaningless. The light speed barrier is not a wall-blocking passage. It is a boundary, beyond which the concept of motion loses all coherent meaning. But before understanding what Feynman discovered about why light speed is the limit, we must first understand exactly what happens as objects approach this barrier. The physics of acceleration toward light speed reveals layer after layer of impossibility, each more fundamental than the last. The barrier is not merely difficult to break, it is mathematically, energetically, and conceptually impenetrable. Picture yourself strapped into the cockpit of an impossible spacecraft. Engineers have built you an engine that violates every practical constraint of real physics. Unlimited fuel, perfect efficiency, thrust that never wavers. Your mission is simple. Accelerate until you break the light speed barrier. You ignite the engines. Acceleration slams you back into your seat as the spacecraft surges forward. The velocity readout climbs steadily. 1% of light speed, 3%, 5%. Each second brings measurable progress. Each unit of fuel burned translates directly into increased velocity. Physics behaves exactly as your intuition expects. At 10% of light speed, you are traveling at roughly 30,000 kilometers per second. Fast enough to reach the moon in 12 seconds. Fast enough to cross the Atlantic Ocean in the time it takes to blink. Yet you are barely crawling compared to your goal. The engines roar steadily. The fuel flows continuously. The velocity climbs. 20%, 30%, 40%. The relationship between fuel consumption and speed gain remains predictable. Your instruments show everything functioning normally. The universe seems willing to let you accelerate forever. Then you cross 50% of light speed and something changes. Your engines have not weakened, your fuel supply remains abundant. The thrust pressing you into your seat feels exactly as strong as before, yet the velocity readout climbs more slowly. Each additional percentage point of speed costs noticeably more fuel than the previous one. The easy linear relationship between energy input and velocity output has broken. You push harder, more fuel, more thrust. The spacecraft shudders with the effort of engines operating at maximum capacity. At 60% of light speed, the velocity gains have slowed further. At 70%, each increment demands substantially more energy than the last. At 80%, the curve steepens dramatically. By 90% of light speed, something extraordinary has happened. Adding the next 10% of velocity to reach the cosmic limit would require more energy than everything you burned to reach 90% combined. Not twice as much. Not 10 times as much. The energy requirement has begun climbing toward infinity. You are not fighting friction. Space is empty. You are not fighting air resistance. There is no air. You are fighting the structure of space-time itself, and space-time always wins. Einstein's special relativity explains exactly what is happening inside your spacecraft. As your velocity increases, your resistance to further acceleration increases proportionally. Early physicists described this as relativistic mass increase. The faster you move, the more massive you effectively become, requiring more force to produce the same acceleration. Modern physicists prefer different terminology. They say your rest mass remains constant, but your relativistic momentum increases without bound. Momentum equals mass times velocity in classical physics. In relativistic physics, momentum equals mass times velocity times the gamma factor. As velocity approaches light speed, gamma approaches infinity, and so does momentum. The gamma factor deserves careful examination because it governs everything strange about relativistic motion. Gamma equals 1 divided by the square root of 1 minus your velocity squared divided by light speed squared. When you are stationary, gamma equals exactly 1. Physics behaves normally. As you accelerate, gamma increases, slowly at first, then rapidly. At 50% of light speed, gamma equals approximately 1.15. Your effective resistance to acceleration is about 15% higher than at rest. Noticeable but not dramatic. The universe has begun pushing back, but gently. At 90% of light speed, gamma reaches approximately 2.3. The same thrust that initially produced significant velocity gains now produces less than half the effect. You are working much harder for diminishing returns. At 99% of light speed, gamma climbs to about 7.1. Every increment of speed now costs 7 times more energy than the same increment would cost at low velocities. Your engines strain against a universe increasingly reluctant to let you accelerate. At 99.9%, gamma exceeds 22. The energy cost per velocity increment has multiplied by more than 20 times compared to rest. You are burning fuel at phenomenal rates for microscopic gains in speed. At 99.99%, gamma surpasses 70. At 99.999%, it exceeds 220. The pattern continues relentlessly. Each additional 9 added to your velocity multiplies gamma by roughly 3. Each multiplication makes the next increment of speed exponentially more expensive. At exactly light speed, gamma reaches infinity. Not a large finite number, not an approximation, mathematical infinity. The energy required to accelerate any massive object to precisely light speed exceeds any finite quantity. It exceeds the total energy content of the observable universe. It exceeds the energy content of 1 billion observable universes. No amount of fuel, no engine efficiency, no technological advancement can overcome mathematical infinity. The Large Hadron Collider demonstrates this principle with breathtaking precision. This 27-kilometer ring buried beneath the Swiss-French border accelerates protons to 99.999991% of light speed. Read those nines carefully. The protons achieve a velocity just 7 parts in 10 billion shy of light speed itself. At this velocity, each proton carries kinetic energy equivalent to a flying mosquito. A mosquito weighs roughly 2.5 milligrams. A proton weighs about 1.7 times 10 to the negative 24th grams. The proton is lighter than the mosquito by a factor exceeding 1 billion, yet both carry the same kinetic energy because the proton's enormous gamma factor multiplies its tiny mass into equivalence with the much heavier insect. Consider what it would take to push those protons, the remaining 7 parts in 10 billion, toward light speed. The energy requirement does not increase gradually. It explodes upward asymptotically. Closing half that remaining gap would require more energy than the collider currently uses. Closing half of the remaining half would require more still. Each halving of the remaining distance demands exponentially more power. To actually reach light speed would require infinite energy. The accelerator would need to tap power sources that do not exist and cannot exist in any finite universe. The barrier is not technological. It is not a matter of funding or engineering or discovering new physics. The mathematics of space-time itself forbids massive particles from reaching light speed through any acceleration process. This mathematical prohibition manifests through multiple interrelated phenomena. Infinite energy requirement is one face of the barrier. Time dilation is another. As your impossible spacecraft approaches light speed, time aboard begins flowing differently than time in the universe outside. This is not a clock malfunction. This is not an illusion. Time itself passes more slowly for rapidly moving observers. At 50% of light speed, time dilation is modest. Your shipboard clocks run about 13% slower than clocks on the launch pad back home. For every hour that passes on Earth, only about 52 minutes pass aboard your spacecraft. The difference is measurable but not dramatic. At 90% of light speed, time dilation becomes substantial. Your clocks run at less than half the rate of stationary clocks. A year of Earth time compresses into about 5 months of shipboard time. You are aging noticeably slower than observers you left behind. At 99% of light speed, the dilation becomes severe. Your clocks run at roughly 14% of normal speed. 7 years pass on Earth for every year you experience aboard the ship. The universe outside is aging rapidly while you cruise through time in slow motion. At 99.9%, your time slows to about 4.5% of external time. A century of Earth time would pass during less than 5 years of your subjective experience. Civilizations could rise and fall while you made a single long voyage. As velocity approaches light speed exactly, time dilation approaches infinity. Time aboard your spacecraft would stop completely relative to the external universe. This is the domain only massless particles can inhabit. Photons exist in this realm of frozen time, but anything with mass is forever excluded. This realm of frozen time belongs only to massless particles. Photons inhabit this domain, but anything with mass is forever excluded from reaching it. Massive particles face the inverse constraint. They can move at any velocity below light speed, from stationary to 99.999999% of the cosmic limit. But they can never reach exactly light speed, because doing so would require their time to stop completely. The constraints reinforce each other, creating a barrier that cannot be circumvented. Length contraction provides yet another perspective on the impossibility of reaching light speed. As objects accelerate, they contract in the direction of motion. This is not compression in any mechanical sense. The atoms are not squeezed closer together by some force. Space itself contracts for the moving observer. At 50% of light speed, an object retains about 87% of its rest length in the direction of motion. A 1-meter rod measures about 87 centimeters to a stationary observer watching it fly past. At 90% of light speed, the contraction becomes dramatic. The rod shrinks to about 44% of its rest length. That 1-meter rod now measures only 44 centimeters to stationary observers. At 99% of light speed, the rod contracts to about 14 centimeters. At 99.9%, roughly 4.5 centimeters. At 99.99%, about 1.4 centimeters. The shrinking accelerates as velocity increases. At exactly light speed, length contraction becomes complete. The rod would have zero length in the direction of motion. It would be compressed into a two-dimensional plane with no extension along its velocity vector. For any object with actual three-dimensional structure, this represents physical impossibility. You cannot have a zero-thickness object that still contains atoms and occupies volume in other directions. Length contraction, time dilation, and infinite energy requirements are not three separate barriers. They are three manifestations of the same underlying truth. Space-time geometry does not contain any path connecting subluminal velocities to luminal or superluminal velocities for objects with mass. The mathematics is not merely difficult. The mathematics says such paths do not exist. Real experiments confirm every prediction of relativistic mechanics with extraordinary precision. Muons created in Earth's upper atmosphere provide particularly elegant confirmation. These unstable particles form when cosmic rays slam into air molecules at altitudes around 15 kilometers. Muons have extremely short half-lives, about 2.2 microseconds. In that brief interval, even traveling near light speed, a muon should cover only about 660 meters before half the population decays. Given their creation altitude and their typical velocities of roughly 99.94% of light speed, muons should decay long before reaching ground level. Classical physics predicts that almost no muons would survive the 15-kilometer journey to sea-level detectors. Yet ground-based instruments detect enormous numbers of cosmic ray muons, far more than non-relativistic calculations allow. Where are these extra muons coming from? Time dilation provides the answer. At 99.94% of light speed, gamma equals roughly 30. Time passes 30 times slower for the muon than for Earth-based observers. From the muon's perspective, the journey from formation altitude to ground level takes only 1/30th as long as Earth observers calculate. Instead of decaying during 50 microseconds of Earth time, the muon experiences less than 2 microseconds. Most survive the journey. Alternatively, consider the muon's reference frame through length contraction. From the muon's perspective, it is stationary, while Earth rushes upward toward it. At 99.94% of light speed, Earth's atmosphere contracts by a factor of 30. The 15-kilometer journey shrinks to 500 meters. The muon easily survives this abbreviated distance before decaying. Both explanations yield identical predictions. Time dilation in Earth's frame and length contraction in the muon's frame are mathematically equivalent descriptions of the same physical phenomenon. The extra muons reaching ground level exactly match relativistic calculations. The predictions are confirmed daily by cosmic ray detectors worldwide. Particle accelerators provide even more precise verification. The magnetic force required to bend a particle's trajectory depends on its momentum. At relativistic speeds, momentum scales with the gamma factor. If momentum followed classical physics, the magnets would need far less strength to guide the proton beams. The accelerator would not function. The beams would fly off course, smashing into tunnel walls instead of circulating smoothly for hours. The magnets are calibrated using relativistic formulas. They must increase in strength as the protons accelerate, compensating for the climbing gamma factor. Each adjustment matches relativistic predictions exactly. If classical physics governed particle motion, the Large Hadron Collider would be an expensive failure. It works precisely because relativity correctly describes nature. The global positioning system provides everyday confirmation that billions of people rely upon without realizing it. GPS satellites orbit at roughly 14,000 kilometers per hour, fast enough to create measurable time dilation. Their onboard clocks run about 7 microseconds per day, slower than identical clocks on Earth's surface due to velocity effects. Gravitational time dilation creates an opposing effect. The satellites orbit higher in Earth's gravitational field, where gravity is weaker. Clocks run faster in weaker gravity. This effect adds roughly 45 microseconds per day compared to surface clocks. The net effect means satellite clocks gain about 38 microseconds per day relative to ground clocks. Without correcting for this discrepancy, GPS position errors would accumulate at roughly 10 kilometers per day. Your navigation app would become useless within hours. The corrections work exactly as relativistic equations predict, providing everyday proof that time dilation is real and that our understanding of it is precise. Given the overwhelming experimental confirmation of relativistic mechanics, creative minds have wondered whether loopholes might exist. Could clever approaches circumvent the light speed barrier even if direct acceleration cannot? Tachyons represent one hypothetical loophole. These theoretical particles would travel permanently faster than light, just as ordinary matter travels permanently slower than light. Tachyons would have imaginary rest mass, a mathematical property that inverts the usual relationship between energy and velocity. While ordinary particles require infinite energy to reach light speed from below, tachyons would require infinite energy to slow down to light speed from above. The concept seems elegant. Perhaps the universe contains two classes of particles separated by an impassable light speed barrier, ordinary matter below, tachyons above, neither able to cross into the other's domain. The problem is causality. In special relativity, faster-than-light travel is mathematically equivalent to backward time travel. Different observers moving at different velocities would disagree about whether a tachyon traveled forward or backward in time. For some observers, a tachyon message would arrive before it was sent. This creates causal loops that destroy logical consistency. You could receive information about future events and use that information to change them. You could prevent the causes that led to your receiving the information. You could observe your own departure from the vantage point of having already arrived. The contradictions multiply without resolution. These are not philosophical puzzles open to interpretation. They are logical impossibilities that break the mathematics of consistent physical law. A universe permitting faster-than-light travel would be a universe without reliable causality. A universe where effects could precede causes, where information could destroy itself by preventing its own creation. Every experiment ever conducted confirms that our universe does not work this way. Causality proceeds in orderly fashion from past to future. Causes precede effects. Information flows forward through time, never backward. The speed of light enforces this logical structure by preventing any causal connection between space-like separated events. No experiment has ever detected a tachyon. No theoretical framework has successfully incorporated them without generating paradoxes. The weight of evidence strongly suggests tachyons are mathematical curiosities rather than physical realities. Quantum tunneling offers another apparent loophole. In quantum mechanics, particles can appear on the far side of barriers they classically could not penetrate. An electron approaching a wall too tall and thick to climb sometimes emerges on the other side anyway. The particle does not go over the barrier or around it. It simply appears beyond it through quantum mechanical magic. Could particles tunnel through the light speed barrier? Could quantum mechanics provide an escape from relativistic constraints? Careful analysis reveals that it cannot. Quantum tunneling does not actually transmit anything faster than light. The confusion arises from how physicists measure tunneling times. A quantum particle approaching a barrier is not a tiny billiard ball. It is a spread-out wave packet with a front edge, a center, and a trailing edge. When part of this wave packet tunnels through a barrier, the transmitted portion is reshaped. The center of the transmitted packet can emerge before the entire front of the incoming packet has entered the barrier. This reshaping creates an illusion of superluminal transmission. The peak of the outgoing wave appears on the far side before the peak of the incoming wave reaches the barrier. Naive interpretation suggests the particle traveled faster than light. But information does not travel at the wave packet's peak. Information travels at the wave packet's front, and the front of the transmitted packet never emerges before causality allows. No signal, no message, no information of any kind travels faster than light through quantum tunneling. The apparent superluminal effect is an artifact of wave mechanics, not a genuine violation of relativistic limits. Experiments in the 1990s tested this explicitly. Researchers sent photons through barriers and measured their tunneling times with exquisite precision. Some initial claims suggested faster-than-light propagation had been observed. Closer analysis revealed the truth. The front of the transmitted wave packet, which carries actual information, always obeyed causality. The reshaping effect made it appear that the packet's center arrived early. But this was measurement artifact rather than superluminal travel. Quantum mechanics respects the light speed limit as rigorously as classical physics. The Alcubierre warp drive represents yet another attempt to circumvent the barrier. Physicist Miguel Alcubierre proposed in 1994 that a spacecraft might never need to travel faster than light locally while still crossing cosmic distances faster than light could travel through normal space. The concept involves contracting spacetime in front of the spacecraft and expanding it behind. The ship rides a wave of distorted spacetime, stationary relative to the local space around it, while that local region itself moves faster than light relative to distant observers. The spacecraft never exceeds light speed within its local spacetime bubble, even while covering superluminal distances overall. The mathematics of general relativity technically permits such solutions. Spacetime can curve and distort in response to mass and energy. Nothing fundamentally prevents the kind of metric Alcubierre described. The problem is energy requirements. Generating an Alcubierre warp bubble would require exotic matter with negative energy density. Such matter would have to produce gravitational repulsion rather than attraction. While quantum mechanics permits small amounts of negative energy under specific conditions, the quantities required for even a modest warp bubble exceed the total positive energy content of the observable universe. More recent analyses suggest even worse problems. The warp bubble's forward edge would accumulate particles and radiation to catastrophic densities. Upon arriving at a destination, dropping the bubble would release this accumulated energy in a blast, potentially sterilizing entire star systems. And passengers inside the bubble could not control it or steer it, because signals from inside cannot reach the bubble's walls faster than light. The Alcubierre drive remains a mathematical curiosity rather than a realistic propulsion concept. No known physics permits generating the required exotic matter at any scale, let alone the planetary masses necessary for useful propulsion. Wormholes offer another theoretical possibility. These hypothetical tunnels through spacetime would connect distant regions, potentially allowing travelers to emerge far from their starting point without crossing the intervening distance. You would enter one mouth of the wormhole and exit the other mouth light years away, never actually traveling faster than light through the wormhole interior. Wormholes appear in solutions to Einstein's general relativity equations. The mathematics permits them to exist, but maintaining a traversable wormhole open and stable would require exotic matter with negative energy density, the same impossible substance the Alcubierre drive demands. Natural wormholes, if they exist at all, would be microscopic quantum fluctuations far too small for any spacecraft or even any particle to traverse. Expanding them to useful size would require physics we cannot achieve, and may be fundamentally impossible. Every proposed loophole encounters the same ultimate obstacle. It is a fundamental property of how space-time connects events. There are no paths through space-time that connect velocities below light speed to velocities at or above light speed for objects with mass. The barrier exists not because something prevents crossing it. The barrier exists because there is nothing on the other side to cross to. Einstein showed us that this barrier exists and demonstrated its mathematical impenetrability. His equations describe precisely what happens as objects approach light speed. They reveal the asymptotic impossibility of reaching it. They predict every experimental observation with extraordinary accuracy. But Einstein did not explain why space-time has this structure. Why is there a cosmic speed limit? Why is that limit exactly 299,792 kilometers per second? What makes this particular velocity so special that the entire fabric of reality enforces it absolutely? Answering these questions requires going deeper than special relativity permits. The explanation emerges from quantum mechanics, from the strange behavior of particles at the smallest scales, from a revolutionary approach to physics developed by Richard Feynman. His insights revealed that the speed of light is not imposed on the universe from outside. It emerges from the deepest principles governing how particles move through space-time. The barrier is not a wall, it is a consequence of quantum reality itself. Richard Feynman walked into Princeton University in the autumn of 1939, carrying a reputation that preceded him. The 21-year-old from Far Rockaway, New York, had already demonstrated an unusual relationship with physics. While other students memorized formulas and followed prescribed methods, Feynman reinvented solutions from scratch. He trusted his intuition over textbooks. He drew pictures when others wrote equations. He asked questions that made professors uncomfortable. His doctoral advisor, John Wheeler, recognized something extraordinary in this brash young man. Feynman did not just solve physics problems. He saw physics differently than anyone else. Where conventional physicists perceived abstract mathematical relationships, Feynman visualized concrete physical processes. Where others calculated through algebraic manipulation, Feynman imagined particles dancing through space and time. This visual imagination would eventually crack open one of the deepest mysteries in physics. Not just what happens when objects approach light speed, but why the universe enforces this limit with such absolute precision. The answer Feynman uncovered did not add new rules to physics. It revealed that the light speed limit was never a rule at all. It was a consequence of how reality itself is constructed at the most fundamental level. The problem Feynman inherited when he began his graduate work seemed almost hopeless. Quantum electrodynamics, the theory describing how light and matter interact, was broken. Physicists had developed the basic framework in the 1920s and 30s. They knew that charged particles like electrons interact by exchanging photons and the quantum particles of light. They had equations describing these interactions, but the equations produced nonsensical answers. Calculate the simplest quantity imaginable, the energy of a single electron sitting alone in empty space. The electron generates an electromagnetic field. That field contains energy. The electron interacts with its own field, affecting its properties. When physicists computed this self-energy using quantum electrodynamics, they got infinity, not a large number, not an approximation that could be refined. The equations insisted that every electron in the universe should have infinite energy, infinite mass, and infinite charge. Obviously, electrons have none of these infinite properties. Something was deeply wrong with the theory. The infinities appeared everywhere physicists looked. Calculate the probability that a photon scatters off an electron. Infinity. Calculate the correction to an electron's magnetic properties from quantum effects. Infinity. Every interesting question produced the same meaningless answer. Quantum electrodynamics seemed to be telling physicists that the universe should not exist in any recognizable form. Some physicists concluded the theory was fundamentally flawed. Perhaps quantum mechanics and special relativity could not be reconciled. Perhaps entirely new physics was required. The crisis persisted throughout the 1930s while the world descended into war and physics talent scattered across continents. Feynman spent the war years at Los Alamos, contributing to the Manhattan Project while his mind continued wrestling with theoretical puzzles. When the war ended and he returned to academic life at Cornell University, he attacked the infinity problem with fresh determination and his characteristic unconventional approach. The breakthrough came through collaboration with Julian Schwinger at Harvard and Shinichiro Tomonaga in Japan, each working independently toward the same goal. They developed a procedure called renormalization that allowed physicists to extract finite, sensible answers from equations that initially produced infinities. The infinities did not disappear. They were absorbed into redefinitions of measured quantities like mass and charge. The logic was subtle but powerful. When we measure an electron's mass, we measure it interacting with its own electromagnetic field. The infinite self-energy contributes to what we call the electron's mass. Rather than calculating this contribution from first principles, physicists could simply use the experimentally measured mass, which already includes all self-energy effects. The infinities vanished into quantities that were determined by measurement rather than calculation. Renormalization worked mathematically, but it troubled many physicists philosophically. It seemed like sweeping infinities under the rug rather than explaining them. Feynman himself remained uncomfortable with the procedure even while using it brilliantly. But Feynman's approach to quantum electrodynamics went far beyond renormalization. He developed an entirely new way of formulating quantum mechanics that revealed deep truths about why the universe behaves as it does. He called it the path integral formulation, though it became more widely known as the sum over histories approach. Classical physics describes motion through deterministic trajectories. A baseball thrown across a field follows one specific path, determined by its initial velocity and the forces acting on it. Given starting conditions, physics predicts exactly where the ball will be at every future moment. Feynman proposed that quantum particles work entirely differently. An electron traveling from point A to point B does not follow a single path. It follows every possible path simultaneously. Every conceivable trajectory, connecting origin and destination, contributes to the electron's behavior. Straight paths, curved paths, paths that loop backward in time, paths that spiral around the galaxy before arriving, paths that zigzag through every point in the universe. All of them. This sounds like mystical nonsense. How can a single particle take infinitely many paths at once? The answer requires abandoning classical intuition entirely and embracing the quantum mechanical concept of superposition. Before measurement, a quantum particle does not have a definite trajectory. It exists in a superposition of all possible paths. Each path has an associated probability amplitude, a complex number encoding both a magnitude and a phase. The amplitude describes how much that particular path contributes to the particle's overall behavior. When you want to calculate something observable, like the probability that the electron arrives at a specific location, you must add up the contributions from all possible paths. Each path contributes its amplitude. The amplitudes are complex numbers that can add constructively or destructively depending on their phases. Here is where classical behavior emerges from quantum strangeness. Paths that wiggle wildly through space have phases that change rapidly. When you add contributions from many such paths, their varying phases cause them to cancel each other out. The wild detours through distant galaxies contribute almost nothing to the final probability because they destructively interfere with each other. Paths close to the classical trajectory have phases that vary slowly and align with each other. Their contributions add constructively rather than cancelling. The electron is most likely found near where classical physics predicts, not because quantum mechanics forces it onto a single trajectory, but because the classical path is where contributions from many similar paths reinforce each other, Feynman demonstrated that his path integral formulation was mathematically equivalent to the standard Schrödinger equation approach to quantum mechanics. Both frameworks make identical predictions for every possible experiment, but Feynman's version provides profoundly different intuitions about what quantum particles are doing. More importantly for our story, the path integral formulation reveals something fundamental about the light speed limit. It explains why this limit exists at the deepest level of physical law. The contribution each path makes to the sum depends on a quantity called the action. The action is calculated by integrating a function called the Lagrangian along the path. For relativistic particles, the Lagrangian depends on how the particle moves through both space and time, with the speed of light appearing as the fundamental parameter connecting spatial and temporal dimensions. When a path includes any segment where the particle moves faster than light, something remarkable happens to its contribution. The action for that segment becomes imaginary rather than real. This causes the amplitude's phase to oscillate infinitely rapidly along the superluminal portion of the path. Infinitely rapid phase oscillation means perfect, destructive interference. Paths containing faster-than-light segments cancel each other out with absolute precision. They contribute exactly zero to any observable quantity. Mathematically, they exist in the sum. Physically, they are completely invisible. This is the quantum mechanical reason nothing travels faster than light. The universe does not post speed limit signs or employ cosmic traffic enforcement. Instead, the mathematical structure of quantum mechanics automatically zeroes out any contribution from superluminal motion. Faster-than-light paths interfere themselves out of existence. Feynman's insight transformed how physicists understand the light-speed barrier. Einstein showed that reaching light speed requires infinite energy and causes infinite time dilation. These mathematical infinities suggested an impenetrable barrier, but Einstein did not explain why space-time is structured this way. Feynman revealed that the barrier is not imposed from outside. It emerges from within. The rules governing how probability amplitudes combine already contain the light speed limit. There is no separate constraint that needs enforcement. The quantum mathematics simply does not permit superluminal contributions to survive the summation process. Consider the profound implication. The light speed limit is not a restriction on otherwise possible motion. It is a statement about what motion means at the quantum level. Paths faster than light do not contribute to reality because they cancel themselves out. Asking how to travel faster than light becomes meaningless. There is no faster-than-light contribution to the quantum sum that could be amplified or exploited. Feynman developed his famous diagrams as practical tools for calculating quantum electrodynamics processes. These deceptively simple pictures encode complex mathematics in visual form, making calculations tractable that would otherwise require pages of algebra. A Feynman diagram represents particles as lines and interactions as vertices where lines meet. Time conventionally flows upward or to the right, while space extends in perpendicular directions. Each line represents a particle propagating through space-time. Each vertex represents an interaction where particles are created, destroyed, or exchanged. An electron emitting a photon appears as a straight electron line with a wavy photon line branching off from a vertex. The electron continues beyond the vertex with different momentum, having transferred some of its energy and momentum to the departing photon. An electron absorbing a photon shows the reverse, with an incoming photon line joining an electron line at a vertex. The electromagnetic force between two electrons appears as photon exchange. Draw two electron lines running roughly parallel through space-time. Connect them with a photon line representing a quantum of electromagnetic energy passing between them. The photon carries momentum from one electron to the other, causing them to deflect. This is how electrons repel each other at the quantum level. Each Feynman diagram corresponds to a precise mathematical expression. The rules for translating diagrams into equations, called Feynman rules, convert visual representations into calculable amplitudes. By drawing all possible diagrams for a process, translating each into mathematics, and adding the results, physicists can calculate the probability of any quantum electrodynamics interaction. The diagrams made previously impossible calculations routine. After Feynman, graduate students could reproduce results that had consumed years of professional research. The diagrams did not change the physics. They made the physics accessible. But Feynman diagrams also illuminate deep truths about virtual particles and the nature of quantum interactions. The photons exchanged between electrons in these diagrams are called virtual photons. They differ fundamentally from the real photons that reach our eyes or trigger our detectors. Real photons satisfy a strict relationship between energy and momentum determined by their zero mass. A real photon with a given energy must have a precisely corresponding momentum. This relationship, derived from relativity, constrains how real photons can behave. Virtual photons are not so constrained. They can carry any combination of energy and momentum, including combinations that would be impossible for real photons. A virtual photon can have more momentum than its energy permits for a real photon, or less, or even carry the wrong sign of energy. This freedom initially seemed to violate conservation laws and undermine the theory's credibility. Critics charged that Feynman diagrams were mathematical tricks rather than physical descriptions. How could particles carry impossible energies and momenta? Feynman explained that virtual particles are not physical objects in the conventional sense. They are computational devices that encode how fields mediate forces. The impossible energies and momenta cancel out in the final sum. What remains after adding all contributions respects conservation laws and all other physical constraints, including the light speed limit. This clarification reveals something important about faster-than-light motion. Virtual particles can mathematically travel faster than light within diagrams, but their contributions combine to produce results that never transmit information faster than light. The intermediate steps of a calculation may include superluminal components. The final answer never does. When two electrons repel each other by exchanging virtual photons, the force between them does not propagate instantaneously. If one electron suddenly moves, the other electron does not instantly respond. The electromagnetic field between them updates at exactly light speed. Information about one electron's motion reaches the other electron at light speed, never faster. Despite the apparent freedom of virtual particles in intermediate calculations, this principle generalizes throughout quantum field theory. Virtual particles can seem to violate rules that constrain real particles, but observable quantities, the things we can actually measure, always respect fundamental limits, including the speed of light. The quantum machinery works out so that causality is never violated in any measurable process. Quantum field theory extends Feynman's insights to all fundamental particles and forces. In this framework, particles are not tiny billiard balls bouncing through space. They are localized excitations of underlying fields that permeate all of spacetime. The electromagnetic field exists everywhere. When that field vibrates in a particular way, we observe the vibration as a photon. The photon is not an object moving through the field. The photon is the field vibrating. Similarly, the electron field exists everywhere. An electron is a localized disturbance in that field, not a separate object placed within it. This field perspective clarifies why photons travel at exactly light speed while electrons travel slower. The electromagnetic field is massless. Its wave equation permits disturbances to propagate only at light speed. Not faster, not slower. Exactly the cosmic limit. A photon must move at light speed because that is the only speed at which electromagnetic field disturbances can propagate. The electron field has mass. Its wave equation includes a mass term that restricts propagation speeds to values below light speed. An electron can move at any velocity up to, but not including, light speed. The more massive a field's associated particle, the lower its maximum propagation speed relative to light speed. This relationship between mass and propagation speed is not imposed by separate constraints. It emerges mathematically from the structure of relativistic quantum field theory. When you write down a field equation that respects special relativity in quantum mechanics, the speed of light automatically appears as the maximum propagation speed for massless fields and the asymptotic limit for massive fields. Feynman and others proved that this structure is not optional. Any quantum field theory consistent with special relativity must have these properties. Attempts to construct theories permitting faster than light propagation invariably produce logical contradictions. Conservation of probability fails. Causality violations create paradoxes. The mathematics refuses to remain coherent. The only consistent quantum field theories are ones where the speed of light emerges as the maximum speed of causality. This is not a constraint added to the theory. It is a consequence of requiring the theory to make sense at all. The light speed limit is built into the foundations of quantum reality. Quantum entanglement appears at first glance to violate the cosmic speed limit. Measure one particle and you instantly know something about its distant partner, regardless of the separation between them. Einstein famously called this spooky action at a distance, and suspected it proved quantum mechanics was incomplete. But entanglement does not transmit information faster than light. The correlation between entangled particles is real and instantaneous. When you measure one particle's spin as up, its partner's spin becomes down at that same moment, even if the partner is on the other side of the galaxy. This correlation appears to ignore the light speed limit entirely. The crucial subtlety involves what you can do with this correlation. You cannot use entanglement to send a message. When you measure your local particle, you get a random result, or down, with equal probability. Your distant partner gets the opposite result, but they also see only randomness from their perspective. To discover that your results are correlated, you must compare measurements. This comparison requires ordinary communication, which travels at light speed or slower. The correlation exists instantly. Knowledge of the correlation travels at light speed. No information exceeds the cosmic limit. Physicists have proven mathematically that entanglement cannot be exploited for faster-than-light communication. The no-communication theorem demonstrates that quantum mechanics preserves causality despite its non-local correlations. Entanglement connects distant particles in mysterious ways, but those connections cannot carry messages backward through time or outward faster than light. This preservation of causality within quantum mechanics is not accidental. The mathematical structure of quantum field theory requires it. Any theory permitting faster-than-light signaling would produce logical contradictions. Quantum mechanics walks right up to the edge of violating causality with its instantaneous correlations, then stops precisely at the boundary where violation would begin. Black holes represent the ultimate expression of the light speed limit. These cosmic objects contain so much mass, compressed into so small a region that escape velocity at their surface equals the speed of light. Since nothing can exceed light speed, nothing can escape. The boundary where escape becomes impossible is called the event horizon. The event horizon is not a physical surface. No membrane or wall exists there. It is a causal boundary, a surface in space-time beyond which events are permanently cut off from the external universe. Light emitted just inside the horizon travels outward at light speed, but makes no progress against the inward curvature of space-time. It remains forever trapped, asymptotically approaching the horizon without ever crossing it from inside to outside. From an external observer's perspective, objects falling into a black hole never quite reach the horizon. Time dilation becomes infinite at the horizon's edge. An infalling astronaut appears to slow down, redden, and fade as they approach the boundary. External observers never see them cross. The astronaut experiences crossing in finite time from their own perspective, but that crossing takes them permanently beyond the observable universe. Once inside the event horizon, the cosmic speed limit becomes a death sentence. The singularity at the black hole's center lies in the future of every internal trajectory, not in any spatial direction. No matter which way you travel inside a black hole, you are traveling toward the singularity, because the singularity is your future, not a location in space. The light speed limit prevents escape because escaping would require traveling backward in time. This connection between event horizons and causality reveals something profound about the light speed limit. They are extreme examples of how causality shapes space-time geometry. The same light speed that prevents you from sending messages backward in time prevents anything from escaping a black hole's interior. The same causal structure that gives time its direction creates regions of space-time permanently isolated from the rest of existence. The cosmic censorship conjecture proposes that singularities are always hidden behind event horizons, never visible to external observers. If true, this would mean the light speed limit protects the universe from the mathematical pathologies that occur at singularities. Causality would maintain cosmic order by keeping the most extreme gravitational phenomena forever hidden from view. Black holes thus serve as cosmic monuments to the light speed limit. They mark the boundaries where causality creates absolute barriers in space-time. No technology, no matter how advanced, can retrieve information from within an event horizon. The speed of light has carved permanent voids in the fabric of existence. Regions as inaccessible as the past or the future of events outside our light cones. Quantum electrodynamics has been tested with extraordinary precision, providing overwhelming confirmation that Feynman's framework correctly describes nature. The most dramatic test involves the electron's magnetic moment, a quantity called the G-factor. Classical physics predicts that an electron spinning in a magnetic field should have a specific G-factor of exactly 1. Early quantum mechanics revised this prediction to exactly 2. Both predictions are close to the measured value but not quite right. Quantum electrodynamics provides corrections to this G-factor, arising from the electron's interaction with virtual photons in its own electromagnetic field. The more diagrams you include, the more precise your prediction becomes. Physicists have computed these corrections to extraordinary precision, including contributions from diagrams containing up to 5 virtual photon loops. The calculation requires evaluating tens of thousands of individual diagrams. The theoretical prediction matches the experimental measurement to better than 1 part in a trillion. 1 part in a trillion. If you measured the distance from New York to Los Angeles using a ruler accurate to 1 part in a trillion, your measurement would be correct to within the width of a single atom. Quantum electrodynamics achieves this level of agreement between theory and experiment. No other theory in the history of science has been tested so precisely and confirmed so completely. Quantum electrodynamics is not approximately correct. It is exactly correct to the limits of our ability to measure and calculate. Every one of its predictions, including the absolute nature of the light speed limit, is verified beyond any reasonable doubt. The standard model of particle physics extends quantum electrodynamics to include all known fundamental particles and forces except gravity. It describes not just photons and electrons, but quarks, neutrinos, the Higgs boson, and the carriers of the weak and strong nuclear forces. The entire framework rests on the path integral formulation Feynman helped develop. Every particle interaction in the standard model obeys the light speed limit. Information never propagates faster than light through any known quantum process. Causality is preserved in every tested prediction. The cosmic speed limit is not a special rule applying to some phenomena. It is universal, emerging automatically from the quantum field theory structure underlying all fundamental physics. The fine structure constant, approximately 1 over 137, quantifies the strength of electromagnetic interactions in quantum electrodynamics. This dimensionless number determines how strongly electrons couple to photons. It appears throughout quantum electrodynamics calculations affecting everything from atomic energy levels to the force between charged particles. Feynman often spoke about the fine structure constant with something approaching awe. Its value cannot be calculated from first principles. It must be measured experimentally. Yet this single number, along with the masses of fundamental particles, determines the entire character of electromagnetic interactions throughout the universe. If the fine structure constant were significantly larger, electromagnetic forces would be stronger. Atoms would be smaller. Chemistry would operate differently. Life, as we know it, might be impossible. If the fine structure constant were significantly smaller, electromagnetic forces would be weaker. Atoms would be larger and less tightly bound. Different chemistry would emerge. Again, life might not be possible. The fine structure constant connects to the speed of light through the fundamental equations of quantum electrodynamics. Both quantities appear together in expressions governing how charged particles interact. The speed of light sets the maximum propagation speed. The fine structure constant sets the interaction strength. Together, they determine the detailed behavior of electromagnetic phenomena at every scale from subatomic to cosmic. Feynman never claimed to understand why the fine structure constant has its particular value. He called it one of the greatest mysteries in physics, a number that clearly matters enormously, but whose origin remains completely unexplained. Understanding why fundamental constants have their specific values remains an open problem in theoretical physics. What Feynman did understand, and demonstrated with mathematical rigor, was that the light speed limit is not separate from these fundamental structures, it emerges from them. The same quantum field theory framework that predicts the electron's magnetic moment with trillion-fold precision also explains why nothing travels faster than light. The speed limit is not a rule imposed on the universe from outside. It is a consequence of the universe being made of quantum fields that must respect relativistic principles. There is no barrier to break because there is no separate domain beyond the barrier. Faster-than-light motion does not exist as a coherent concept within quantum field theory. Feynman approached all of physics with irreverent curiosity. He famously said that if you think you understand quantum mechanics, you do not understand quantum mechanics. He delighted in the strangeness of the quantum world while insisting on mathematical precision and experimental verification. His path integral formulation did not just solve practical calculation problems. It revealed that quantum mechanics and special relativity fit together in a specific way that makes the light speed limit inevitable. The apparent barrier is actually a structural feature of reality at its most fundamental level. Nothing in physics forbids faster-than-light travel the way a law forbids jaywalking. Instead, the quantum structure of space-time makes superluminal motion literally meaningless. There is nothing there to travel to, no path through the quantum sum that contributes to observable reality. This is what Feynman actually uncovered. Not a new constraint on motion, not a deeper barrier. Rather, he showed that the light speed limit was never really a limit in the prohibitive sense. It is a description of how quantum amplitudes combine to create the reality we observe. Faster-than-light paths cancel themselves out of existence before they can contribute anything to the physical world. The mathematics Feynman developed continues to underpin all successful theories of fundamental physics. His diagrams remain standard tools in every particle physicist's toolkit. His path integral formulation provides the foundation for string theory, quantum gravity research, and theoretical physics frontiers far beyond what existed in his lifetime. And all of it confirms the same deep truth. The speed of light is not the universe's speed limit. The speed of light is the speed at which the universe updates itself, the rate at which cause can produce effect, the fundamental tempo of reality. Nothing travels faster, because faster has no meaning in the quantum mechanical structure from which space-time emerges. Feynman died in 1988, having transformed physics multiple times across his career. He worked on the atomic bomb, developed quantum electrodynamics, explained superfluidity in liquid helium, proposed quantum computing decades before it became practical, and contributed to understanding the weak nuclear force. Each achievement would have secured a lasting reputation for any scientist. Together, they established Feynman as one of the most important physicists of the 20th century. But his most profound contribution may be the understanding that the light speed limit is woven into existence at the quantum level, built into the fundamental rules governing how probability amplitudes combine to produce observable reality. What remains is understanding what this means. If the speed of light is the speed of causality, not just a property of electromagnetic radiation, then what does this tell us about the nature of space, time, and the universe itself? The final piece of the puzzle reveals that the cosmic speed limit shapes everything from the arrow of time to the structure of the observable cosmos. The barrier is not just a feature of physics, it is the foundation upon which physical reality is constructed. The speed of light has nothing to do with light. This statement sounds paradoxical until you understand what physicists actually discovered. Photons travel at this velocity because they happen to be massless, not because the speed belongs to them. Any massless particle travels at exactly the same rate. Gravitons, if they exist, would travel at this speed. Gluons travel at this speed within the confines of atomic nuclei. The cosmic speed limit existed before the first photon ever flickered into existence during the universe's earliest moments. The proper name for this fundamental constant is the speed of causality. It represents the maximum rate at which any cause can produce any effect anywhere in the cosmos. Every interaction, every force, every transfer of information must obey this limit. Not because some cosmic enforcement mechanism prevents violations, but because causality faster than this rate has no coherent meaning within the mathematical structure of space-time. Consider what causality actually means, stripped down to its essence. One event influences another. A rock strikes a window. The window shatters, the striking precedes the shattering. The striking causes the shattering. This temporal ordering and causal connection seems so obvious that we rarely examine it carefully. But this relationship requires something profound. Information about the rock's motion must reach the window's location before the window can respond. The window cannot shatter in anticipation of a rock that has not yet arrived. Effect cannot precede cause. The causal connection propagates through space at some finite speed, and that speed has an absolute maximum. Nothing in the universe can transmit cause to effect faster than 299,792 kilometers per second. Not electromagnetic forces, not gravity, not the strong nuclear force binding quarks into protons. Not any mechanism physicists have discovered or imagined. The limit is universal, applying equally to every known phenomenon. When you push one end of a rigid rod, the other end does not move instantaneously. Your push creates a compression wave that travels through the material at the speed of sound in that substance. Steel transmits compression waves at about 5 kilometers per second. The far end of a 1-meter steel rod begins moving about 0.2 of a millisecond after you push the near end. This delay is imperceptible to human senses, but absolutely real. Even if you constructed a rod from the stiffest conceivable material, the compression wave could never exceed light speed. The speed of sound in any material must remain below the speed of light, because sound waves transmit information, and information cannot travel faster than causality permits. This might seem like an engineering constraint rather than a fundamental law. Perhaps some exotic material could transmit forces faster. Perhaps some clever mechanism could circumvent the limit, but every attempt to construct such mechanisms collapses into logical contradiction. The speed of causality is not a barrier imposed on otherwise unlimited possibilities. It is a structural feature of reality itself. Special relativity reveals why this limit protects the logical structure of cause and effect. Einstein discovered that space and time are not separate absolute quantities, but interwoven aspects of a unified space-time fabric. Different observers moving at different velocities measure different amounts of space between events. They measure different amounts of time between events. These disagreements are not errors or illusions. They are genuine features of how space-time works. Events that cannot causally influence each other occupy what physicists call space-like separation. For such events, something extraordinary occurs. Different observers disagree about which event happened first. One observer watching events A and B might see A occur before B. Another observer, moving at a different velocity, might see B occur before A. A third observer might see them as simultaneous. This temporal ordering reversal sounds deeply disturbing. How can the sequence of events depend on who is watching? Does the universe not have an objective ordering of occurrences? The answer is both yes and no. For events that can causally influence each other, all observers agree on temporal ordering. If event A causes event B, every observer in the universe sees A happen before B. The causal sequence is absolute and objective, but for events that cannot causally influence each other, the universe does not define an objective ordering. Neither event causes the other. Neither event affects the other. The question of which happened first has no absolute answer, because the question itself assumes a connection that does not exist. This is where the speed of light becomes essential. Light speed defines the boundary between events that can causally connect and events that cannot. If the spatial separation between two events exceeds the distance that light could travel during their temporal separation, those events are space-like separated. Neither can cause the other. Their temporal ordering is observer-dependent. If the temporal separation exceeds the time light would need to cross their spatial separation, the events are time-like separated. They can causally influence each other. Their temporal ordering is absolute. Events separated by exactly the distance. Light travels during their temporal separation are light-like separated. They lie on each other's light cones. A light ray, leaving one event, would arrive precisely at the other. This classification creates the geometric structure of space-time causality. Every event in the universe sits at the apex of a double cone, extending into past and future. The future light cone contains every event this event could potentially affect. The past light cone contains every event that could potentially have affected this one. Everything outside both cones is causally disconnected, unreachable and unreaching. Your future light cone at this exact moment contains every location you could possibly influence through any action you take. If you switched on a powerful laser right now, the beam would expand outward at light speed, defining the boundary of your influence. Anything outside that expanding sphere cannot be affected by anything you do. Your past light cone contains everything that could possibly have contributed to your current state. Light from distant stars that entered your eyes shaped your neural patterns. Cosmic rays from ancient supernova triggered mutations in your ancestors' DNA. But only events within your past light cone could have played any role. Everything outside is causally irrelevant to your existence. The speed of light determines the shape of these cones. A faster light speed would expand the cones, enlarging the causally connected region. A slower light speed would contract them, shrinking the domain of possible influence. The particular value we observe creates the particular causal structure our universe possesses. Faster than light travel would transform space-like separations into causal connections. This is not merely prohibited by some cosmic rule. It creates logical paradoxes that cannot be resolved within any consistent framework. If you could travel faster than light, you could reach events in your space-like separated region. But those events have ambiguous temporal ordering. Some observers see them as being in your future. Others see them as being in your past. By traveling to such events, you transform observer-dependent temporal ordering into objective causal connection. The mathematics of special relativity shows that faster-than-light travel is equivalent to backward time travel. Different observers would disagree about whether your journey went forward or backward in time. For some observers, you would arrive at your destination before you departed from your origin. You would exist at your destination without having yet begun your journey. This creates causal loops that destroy logical consistency. You could receive information about future events and use that information to change them. You could prevent the causes that led to your receiving the information. You could observe your own departure from the vantage point of having already arrived. The contradictions multiply without resolution. These are not philosophical puzzles open to interpretation. They are logical impossibilities that break the mathematics of consistent physical law. A universe permitting faster than light travel would be a universe without reliable causality. A universe where effects could precede causes, where information could destroy itself by preventing its own creation. Every experiment ever conducted confirms that our universe does not work this way. Causality proceeds in orderly fashion from past to future. Causes precede effects. Information flows forward through time, never backward. The speed of light enforces this logical structure by preventing any causal connection between space-like separated events. The geometry of space-time encodes the light speed limit directly into its mathematical structure. Physicists describe space-time using a quantity called the interval, which combines spatial distance and temporal duration into a single measure. The interval between two events equals the time separation squared multiplied by light speed squared minus the spatial separation squared. This interval has a remarkable property that shocked physicists when Einstein first demonstrated it. The interval is invariant. All observers, regardless of their motion, calculate the same interval between any two events. They disagree about spatial separation. They disagree about temporal separation. But they agree on the interval. The invariance of the space-time interval defines the geometry of our universe. It is not Euclidean geometry, where the Pythagorean theorem applies to spatial distances. It is Minkowskian geometry, where a modified Pythagorean theorem applies to space-time intervals. The speed of light appears in this fundamental geometric relationship as the conversion factor between spatial and temporal dimensions. When we say light travels at 300,000 kilometers per second, we are really expressing a geometric truth about space-time. 1 second of time is equivalent to 300,000 kilometers of space in the unified fabric of space-time geometry. These are the natural units. An object traveling at light speed moves 1 unit of space for every unit of time. The speed of light is not a velocity in the conventional sense of distance covered over time. It is the conversion factor between distance and time, the exchange rate that lets physicists express temporal durations in spatial units and spatial distances in temporal units. Physicists often work in units where light speed equals exactly 1, eliminating the conversion factor entirely and revealing the underlying unity of space and time. Einstein's famous equation E equals mc squared contains this same conversion factor. Mass and energy are not merely related, they are identical quantities measured in different units. The speed of light squared provides the conversion between mass units and energy units. 1 kilogram of mass contains about 90 quadrillion joules of energy. This staggering number reflects the enormous conversion factor between our everyday units of mass and energy. The speed of light squared equals approximately 9 times 10 to the 16th power in metric units. Multiplying any mass by this factor yields its energy equivalent. Nuclear reactions exploit this equivalence. When uranium atoms fission, roughly 0.1% of their mass converts to energy. This tiny fraction multiplied by the enormous conversion factor produces the devastating power of nuclear weapons and the controlled output of nuclear power plants. The same conversion factor explains why the sun can burn for billions of years by converting a small percentage of its hydrogen mass into radiant energy. The speed of light also governs gravitational phenomena with equal absoluteness. Einstein's general relativity extended special relativity to include gravity, revealing that massive objects curve the space-time around them. This curvature is what we experience as gravitational attraction. When a massive object moves, the curvature of space-time around it must change. How fast can this change propagate? The answer is exactly light speed. Gravitational disturbances travel through space-time at the same velocity as electromagnetic disturbances. Gravitational waves provide spectacular confirmation. When massive objects accelerate violently, they create ripples in space-time that spread outward like waves on a pond. These gravitational waves were predicted by Einstein in 1916, but not directly detected until 2015, when the LIGO observatories measured waves from colliding black holes over 1 billion light-years away. The LIGO detection allowed physicists to measure the speed of gravitational waves with extraordinary precision. The waves arrived at detectors separated by thousands of kilometers, at times differing by milliseconds. The measured propagation speed matched light speed to better than 1 part in a million billion. Gravity and electromagnetism travel at exactly the same velocity. This equivalence is not coincidence. It reflects the fundamental nature of the speed of light as the speed of causality itself. All forces mediated by massless particles must propagate at this velocity. Photons mediate electromagnetic forces. Gravitons, the hypothetical quantum particles of gravity, would be massless, and therefore must travel at light speed. Any force carried by a massless mediator faces the same constraint. The universality of the light speed limit suggests something profound about its nature. It is not a property of light that happens to apply to other phenomena. It is a property of space-time itself that all phenomena must respect. The speed of light is the speed at which space-time updates, the rate at which the universe can change from one configuration to another. This perspective transforms how we understand the cosmic speed limit. It is not a barrier preventing faster motion. It is the fundamental tempo of reality, the maximum frame rate at which existence can process change. Asking why nothing moves faster than light is like asking why reality cannot update faster than it updates. The question contains its own answer. The cosmic speed limit shapes the large-scale structure of the universe in ways most people never consider. The observable universe has a boundary, not because space ends, but because light from beyond certain distances has not yet had time to reach us. This cosmic horizon lies approximately 46 billion light-years away in every direction. The number seems paradoxical. The universe is only about 13.8 billion years old. How can the observable horizon be 46 billion light-years away if light has only been traveling for 13.8 billion years? The answer involves cosmic expansion. The universe has been stretching since the Big Bang. Light that left a distant region 13 billion years ago traveled through space that was expanding. As the light crossed it, by the time that light reaches Earth, the region that emitted it has been carried much farther away by cumulative expansion. The source is now 46 billion light-years away, even though the light traveled for only 13.8 billion years. Beyond the cosmic horizon lie regions we can never observe. They almost certainly contain galaxies, stars, planets, possibly even intelligent civilizations. But no information from those regions has reached us because light speed limits information transfer, and the universe is too young for light from those distances to have arrived. The situation grows more severe as cosmic expansion accelerates. Dark energy, the mysterious component driving acceleration, is pushing distant galaxies away from us ever faster. Galaxies beyond a certain distance are receding faster than light speed relative to us, not because they are moving through space faster than light, but because the space between us is expanding at rates that exceed light speed across such vast distances. These distant galaxies have already crossed beyond our cosmic horizon. We can still see the ancient light they emitted billions of years ago, but no light they emit today will ever reach us. They are causally disconnected from our future. Anything that happens in those galaxies cannot affect us. Anything we do cannot affect them. The speed of light has permanently isolated vast regions of the universe from each other. Eventually, the accelerating expansion will carry almost all galaxies beyond our horizon. In approximately 100 billion years, only galaxies gravitationally bound to our local group will remain visible. The rest of the cosmos will have vanished beyond a horizon that continues receding as expansion accelerates. Future astronomers in that distant era might conclude they live in an island universe, a single galactic group surrounded by absolute emptiness. They would have no evidence of the Big Bang because the cosmic microwave background radiation will have redshifted beyond detection. They would have no evidence of cosmic expansion because all visible galaxies would be gravitationally bound and moving toward each other. The speed of light, combined with accelerating expansion, will have erased the evidence of cosmic history. This cosmic isolation connects to deep questions about entropy and the arrow of time. The second law of thermodynamics states that entropy, the measure of disorder, increases over time in closed systems. Hot coffee cools, organized structures decay. The universe evolves from ordered to disordered states. This entropy increase defines the direction of time, the arrow pointing from past to future. But why does entropy increase toward the future rather than the past? The fundamental laws of physics are mostly time-symmetric. Running them backward produces equally valid physics. Nothing in the equations themselves picks out a preferred direction of time. The answer involves information spreading, and the speed of light plays a crucial role. Any localized low-entropy configuration tends to evolve toward higher entropy because there are vastly more high-entropy states than low-entropy states. But this evolution requires information about the local configuration to spread outward, establishing correlations with the surrounding environment. Information spreads at speeds up to but not exceeding light speed. This spreading carries correlations outward from any local region, increasing the total entropy of the combined system. The speed of light determines how quickly these correlations can establish, which in turn determines the rate of entropy increase across cosmic scales. A universe with a different speed limit would have a different thermodynamic character. A slower speed would slow entropy increase, potentially allowing structures to persist longer. A faster speed would accelerate thermalization, potentially preventing complex structures from forming at all. We exist in a universe where the speed of causality permits stars to burn for billions of years before thermodynamic equilibrium claims them. It permits planets to cool and chemistry to complexify. It permits life to evolve through countless generations before heat death arrives. This may not be coincidence. The anthropic principle suggests that observers can only exist in universes with parameters compatible with observer existence. Universes with radically different light speeds might not permit the formation of stars, planets, or beings capable of asking why light speed has its particular value. We observe this light speed because it is among the values allowing observers to exist. This reasoning does not explain why our universe has this light speed, rather than some other value. It merely explains why we should not be surprised to find ourselves in a universe with a value compatible with our existence. The deeper question of why fundamental constants have their particular values remains one of the great unsolved problems in physics. The speed of light connects to quantum mechanics through relationships that go beyond what Feynman's path integrals reveal. The uncertainty principle, discovered by Werner Heisenberg, sets fundamental limits on how precisely certain pairs of quantities can be simultaneously known. Position and momentum form one such pair, energy and time form another. These uncertainty relations involve Planck's constant, the fundamental quantum of action, but when relating energy to momentum for relativistic particles, the speed of light appears as the essential conversion factor. The uncertainty principle in its relativistic form requires light speed to connect the spatial and temporal aspects of quantum uncertainty. Quantum field theory unifies quantum mechanics with special relativity, and this unification only works at a specific speed. Attempts to construct quantum theories where fields propagate faster than light invariably produce logical inconsistencies. Probabilities become negative, conservation laws fail, causality violates itself. The mathematics refuses to cohere. The only consistent quantum field theories are ones where light speed emerges as the maximum propagation speed for all fields. This is not an added constraint. It is a consequence of requiring the theory to remain logically consistent. The quantum nature of matter and the relativistic structure of space-time fit together only at this particular cosmic speed. Some speculative theories propose that the speed of light might vary across cosmic time or space. Perhaps light was faster in the early universe. Perhaps it differs in distant regions. These variable speed of light theories attempt to address certain cosmological puzzles without invoking cosmic inflation. Experimental tests have searched for evidence of varying light speed with extraordinary precision. Laboratory measurements test whether light speed depends on direction or local conditions. So far, every test confirms that light speed is constant to the limits of measurement precision. A varying light speed would revolutionize physics. Fundamental constants would not be constant. The structure of quantum field theory would require revision. The foundations of cosmology would need reconstruction. The implications would cascade through every branch of physics. The speed of light represents humanity's ultimate constraint. We will never visit stars in distant galaxies within human lifetimes, using any technology that respects known physics. The nearest major galaxy, Andromeda, lies 2.5 million light-years away, even travelling at 99% of light speed. A journey there would require 2.5 million years of Earth time. Time dilation would shorten the journey for travellers, but they would return to find Earth millions of years older, everyone they knew long dead, human civilization unrecognisably transformed or extinct. Interstellar travel within our own galaxy faces similar constraints at smaller scales. The nearest star system, Alpha Centauri, lies 4.4 light-years away. A spacecraft travelling at 10% of light speed, which exceeds any propulsion system we can currently envision, would require 44 years to arrive. Travellers would return to find their friends aged, their children elderly, their world changed. Communication across cosmic distances encounters the same limit. A message sent to a civilization in another galaxy would require millions of years to arrive. A reply would take millions more. Meaningful conversation with beings in distant galaxies is impossible even in principle. The speed of light isolates cosmic civilizations from each other as effectively as walls of impenetrable matter. This isolation extends to regions of our own observable universe. A message sent today to a galaxy 10 billion light-years away would never arrive because cosmic expansion carries that galaxy beyond our reach faster than light can cross the intervening space. We are cosmically alone not because the universe lacks other civilizations, but because the universe makes communication between distant civilizations impossible. Yet the constraint that isolates us also enables us. Without the light speed limit, causality would collapse into paradox. Effects could precede causes. Information could travel backward through time. The orderly sequence of events from which meaning emerges would dissolve into logical contradiction. Our very ability to think requires causality. Neural signals must travel in sequence through our brains. Causes in the form of sensory inputs must produce effects in the form of perceptions and responses. Memory must record the past rather than the future. Consciousness itself depends on the temporal structure that light speed enforces. A universe without a cosmic speed limit would be a universe without reliable causality. Random events in the distant future could retroactively change the past. Information about choices not yet made could influence the decisions that create them. Existence would become incoherent. Richard Feynman understood this deeply. His path integral formulation showed that faster-than-light contributions cancel themselves out of quantum calculations. His diagrams encoded causal structure into the mathematics of particle physics. His entire approach to physics embedded the speed of light as the tempo of reality itself. The barrier is not a wall preventing passage. The barrier is a structural feature of how existence works. There is no other side to break through to, because faster-than-light motion is not a coherent concept within the mathematical framework describing reality. Asking how to exceed light speed is like asking how to find a point north of the North Pole. The question assumes something that does not exist. You are reading these words in a universe governed by absolute constraints we did not choose and cannot change. The speed of light marks the boundary of causality, the geometry of space-time, the structure of quantum fields, and the ultimate limits of human reach. Nothing we build can circumvent these limits. Nothing we discover can abolish them. They are woven into existence at a level deeper than matter, deeper than energy, deeper than space and time themselves. The speed of light is not a constraint imposed on reality from outside. The speed of light is what makes reality possible. It is the tempo at which existence updates, the frame rate of the cosmos, the fundamental rhythm underlying every phenomenon, from quantum fluctuations to galactic collisions. Feynman spent his career showing how this rhythm emerges from the deepest principles of physics. His path integrals demonstrated that faster-than-light contributions vanish from quantum calculations. His diagrams encoded causal structure into particle physics. His entire framework revealed that the cosmic speed limit was never a separate rule. It was always a consequence of how quantum fields and relativistic space-time fit together. The universe does not prohibit faster-than-light travel. The universe is constructed from components for which faster-than-light travel is meaningless. There is nothing to prohibit because there is nothing there to prohibit. And so, we find ourselves in a cosmos of absolute boundaries. The past light cone contains everything that could have shaped our existence. The future light cone contains everything we could possibly affect. Beyond both cones lies the vast majority of space-time, causally disconnected from us, forever beyond our influence or perception. This is not a tragedy, it is the price of coherent existence. Without the light speed limit, reality would dissolve into paradox. With it, we have stars and planets and civilizations and minds capable of understanding why the universe works as it does. The speed of light is the cosmic metronome, the universal constant that establishes the tempo of existence. Every photon, every graviton, every ripple through any quantum field marches to this beat. The universe cannot accelerate its tempo. The tempo is not separate from the universe. The tempo is what the universe is. Feynman showed us why, Einstein showed us how, and both showed us that this limit is not our prison. It is our foundation. The very ground on which we stand exists because causality flows in one direction at one maximum speed through the unified fabric of space-time. The barrier that confines us is the barrier that creates us. And understanding that barrier is understanding the deepest truth physics has uncovered about the nature of existence itself.